In this video, we are going to study section 4 for intermolecular forces. At the end of this section, you will be familiar with these terms: London dispersion forces, dipole-dipole forces, and hydrogen bonding. These are the key terms for this section. And at the end of this section, you must be able to deduce the type of the intermolecular forces present in the substance based on their structure, chemical formula, and polarity. And also you must be able to predict and explain physical properties of the covalent compounds, like their volatility, electrical conductivity, solubility, their boiling point and melting point, in terms of their structure and intermolecular forces which are available between them. Okay, so let's start this section. We want to talk about intermolecular forces. So intermolecular forces are the forces which exist between the molecules. Look at this picture which is available at the left side of the screen. Two types of the attractions are available between the molecules. One is written intramolecular. Intramolecular, it means inside the molecule, and those actually the covalent bonds which forms between the atom, resulting from sharing of the electrons. Intermolecular forces are forces which are available between the two molecules, or usually more than two molecules. The strength of these intermolecular forces determines the physical properties of the molecules. Like, for example, if they are volatile or not. Volatile means if they can easily go to the gas and vaporize or not. It also can explain about the solubility of them, about the conductivity, and about the melting point. All of these properties depends on the intermolecular forces which are available between the molecules. Okay, so let's talk about these forces which are available between the molecules. The first type of the forces that we want to talk about is London dispersion force. What is the London dispersion force? This is the type of the force available between all of the molecules, but it's very important for non-polar molecules. As you know, the non-polar molecules are the molecules which don't have the dipole. So the electron clouds are evenly distributed between the molecules, and you don't have negative and positive area in the molecule. Okay, so I draw here several non-polar molecules. Suppose they are CH4, okay, or Cl2, no matter which one of them we are drawing. Both of these molecules are nonpolar. And also we can talk about the atoms. For example, the helium atom. The helium atom has the nucleus, which is composed of the two protons, and in one s orbital two electrons are moving randomly there. Okay, so again, in the helium atom also, these electrons are evenly distributed in one s orbital. So we can say the helium atom is also nonpolar. Actually, this happens for all of the atoms. The atoms are nonpolar because the electrons in their electron clouds uniformly distributed in the orbitals around the nucleus. Okay, so what type of the attraction are available between these non-polar molecules? So let's go back to see the structure of the ionic compound. In the ionic compound, you have cation, anion, cation, anion. So you have alternatively cation and anion. And you know you have electrostatic attraction between these cation and anion, positive and negative charge, which is known as the ionic bond. So here the ionic bond, or attraction between the oppositely charged particles or oppositely charged ions, keep them together. But what about non-polar molecules? In the non-polar molecules, we don't have positive and negative area. So what happens in this case? Okay, as we said, around the nucleus in the atoms and also in the molecular orbitals, in the hybrid orbitals in the molecules, the electrons are moving uniformly in our direction. But what happens? Sometimes at a moment, the number of the electron in one side of the molecule becomes more than the electrons which are available in the other side of the molecule. So at that moment, the side of the molecule which you have extra electron becomes partially negative and the other side of the molecule becomes partially positive. This is temporary. So what happens here? Here a dipole is formed, but we call it instantaneous dipole, okay, or temporary dipole. So here we have temporary dipole. Temporary dipole forms because the electrons are moving randomly and there is the chance that at an instant of time the number of electrons on one side of the molecule be greater than the other side. So that side of the molecule becomes negative, other side of the molecule becomes positive. When this temporary dipole happens, this dipole induce dipole on the adjacent molecule. So what happens to the neighboring molecule? In the neighboring molecule also electrons are moving randomly here. Okay? But when this side of the molecule becomes negative, it pushes away the electron which are here. So the electron goes to the right side. So this side of the molecule depletes from the electron, becomes partially positive. The other side of the molecule becomes partially negative. So this temporary dipole has induced dipole on adjacent molecule. And you can see now we have two dipoles. Both of them are temporary, but the negative and positive side of these dipoles or molecules are close to each other. So there are some type of attraction happens between them, which we call it London dispersion force. So this is London dispersion force. Let's go back to your book. Okay, here. So here it shows the London dispersion force in the chlorine molecule. So what is written here says instantaneous dipole. It means by chance one side of the molecule will have more electron than the other side. So this side of the molecule becomes partially negative, the other side becomes partially positive. This one induced the dipole on the other one. Okay, so this negative area push the electron to the other side of the molecule. So this side of the neighbor molecule becomes partially negative, this side becomes partially positive. So there would be some attraction between them, which is the London dispersion force. But because the electrons are keep moving, this is very temporary, and you can see here again you don't have any dipole here. So this type of the dipole, it forms and disappears, forms and disappears. That's why the London dispersion forces which are available here is very weak, okay, because forming, disappearing, forming and disappearing. So after a time, again, because the electrons are moving, again you have the separation of the charge within the molecule. So look what happens here. This time, this side of the molecules has more electron than the other side of the molecule. So here becomes partially negative, other side becomes partially positive. Here, which is partially negative, push the electron away from here on adjacent molecule. So this area of adjacent molecule becomes negative, this area becomes positive. Again, you can have some sort of the attraction between them. This positive attracts to the negative area, this negative area attracts to the positive area. So this is the London dispersion force. After a moment, again the direction of the London dispersion force change. Okay, so this is the London dispersion force, and it's very important for non-polar particles, because in the non-polar particles or the non-polar molecules, this is the only source of the attraction between them. Okay, so what you must know about the London dispersion force, it occurs between opposite end of the two temporary dipole. Okay, so the dipole which forms here are temporary dipole. And one more thing, this temporary dipole does not last for more than an instant. Okay, so it forms for small short amount of the time, because as the electron density is continuously changing, but it may influence the electron distribution in neighboring atom or molecule, causing induced dipole. So when this temporary dipole forms on one of them, it induces the dipole on the adjacent molecule. Okay, so this is the normal distribution of the electron cloud for the chlorine. So the electron cloud is evenly distributed all of the chlorine molecule, but for some instant, the number of the electrons on one side of the molecule becomes more than the other side. This side becomes partially negative, other side becomes partially positive, and this induces the dipole on the other one. So the dipole is induced in the neighboring molecule, and then you have attraction between these two temporary dipoles, which we call it London dispersion force. And as I said, in the non-polar molecule, this is the only force which are available between them. But the non-polar molecules, they have low melting point and low boiling point. What does it show you? It means you can easily separate the molecule from each other. It means the force which are available between the non-polar molecules, in other words, the London dispersion forces, are very weak. Okay, so you need a small amount of energy to separate them. So that's why I say little energy is required to break the weak London dispersion forces and separate the molecules from each other. So when you separate the molecules from each other, they become gas. That's why at room temperature there are enough heat or thermal energy to overcome the attraction or London dispersion force between the non-polar molecules. That's why most of the non-polar molecules like O2, Cl2, CH4, N2, carbon dioxide are gas at room temperature. But what the London dispersion force and its strength depends on. The strength of the London dispersion force depends on the size of the molecule. Or it's better to say it depends on the number of the electrons which are available there. If the number of the electron in the molecule increases, by random movement of the electron, the probability of forming temporary dipole increases. That's why if you have non-polar molecules and you want to compare their boiling point or melting point, you have to check their molar mass. The one which has greater molar mass has more electron, and the chance of forming temporary dipole increases. So the London dispersion force for that molecule becomes bigger. So it's shown in these tables that you have here. So look at the first table. What do you have in the first table? You have the halogens: fluorine, chlorine, bromine, iodine. You know that when you are going down the group, the molecule becomes bigger, the molar mass increases. So as the molar mass increases, look at their boiling point. Negative 188, then it becomes negative 34, 59, 185. So you can see their boiling point increases. This shows that the London dispersion force, which is available between these nonpolar molecules, is increasing by the size of the molecule. So that's why at room temperature, the first two halogens are gas, the next one is liquid, and the iodine becomes solid. Okay, and the next table shows the same thing for the alkane. Alkane are hydrocarbons which are non-polar. By increasing the number of the carbon in alkane, the size of the molecule becomes bigger. The molecule will have more electron. And because London dispersion force increases when the molecule is bigger and more massive, you can see the boiling point of the hydrocarbon also increases by increasing the size of the molecule. So it's very important to be able to compare the boiling point and attraction between two nonpolar molecules based on their size. Another result of the London dispersion force is that we can liquefy nonpolar molecules. For example, nitrogen N2 can be liquefied at negative 192. And also helium, which is atom, and we said the atoms are nonpolar, it can be liquefied at negative 269 degrees. So when they become liquid, you know that in the liquid the molecules are close to each other, or atoms are close to each other, and the attraction between them, there are some attraction between them. So when you decrease the temperature, the heat energy which is available at low temperature is not enough to overcome even weak London dispersion force. So the London dispersion force is able to keep the molecules or atom close to each other at low temperature. So you can liquefy non-polar molecules. London dispersion force, as we said, is not only available between non-polar molecules, but they are also available between the polar molecules. But it's less significant in the polar molecules, because in the polar molecules we have stronger forces. So compared to these stronger forces which is available between the polar molecules, London dispersion forces are negligible. Okay, so let's move on and talk about these stronger forces which are available between the polar molecules. So you know that the polar molecules, they have permanent dipole. It means for the polar molecule, always one side of the molecule is partially negative, the other side of the molecule is partially positive. It's shown HCl as an example here. So the polar molecule, they have permanent dipole. Okay, so you have a lot of molecules, each one of them has permanent dipole. So the negative side of one molecule is attracted to the positive side of the adjacent molecule. This is called dipole-dipole attraction. So the dipole-dipole attraction available only between the polar molecule, and this type of the attraction is absent in the non-polar molecules. The strength of the dipole-dipole attraction is more than London dispersion force, because the dipole-dipole attraction is permanent, but the London dispersion force are temporary, and it's a result from the temporary dipoles. Okay, so the strength of this intermolecular force depends on the distance between two molecules, and also orientation of these two dipoles, relative orientation of these two dipoles. Okay, if you have a polar molecule, their melting point and boiling point usually is more than non-polar molecule with the same mass, because dipole-dipole attraction is more than non-polar than London dispersion force, which are available between the non-polar molecules. Look at this table. This table compares C3H8 and CH3OCH3. If you look at the structure of these two, I draw the structure here, C3H8. Okay, so you have carbon, connects to carbon, connects to carbon. This is the structural formula for them. This is propane, and the propane is non-polar molecule. Okay, so this non-polar molecule. So the only force between the propane and another propane is London dispersion force, which is very weak. But CH3 or CH3, this is the ether. Okay, so if I want to draw it in expanded format, something like this. Around the hydrogen you have the bent molecule, because it has two dipole and it has four domain. Okay, the polarity of this bond is in this direction, the polarity of this bond is in this direction, so the molecule becomes polar. Here the molecule is polar. Around the oxygen you have partially negative, and around here, around CH3s, you have partially positive. It's somehow like the water molecule. So we have two type of the molecule here. One of them is non-polar, the other one is polar. You can see their molar mass are same for these two, the molar mass 44 and 46. So we say they have comparable molecular mass. So when the molecular mass are close to each other, it means the London dispersion force which are available between all of the molecules is almost same for both of them. But for this molecule which is polar, it has extra attraction between its molecule, and that is dipole-dipole attraction. So when you look at the boiling point, you can see that the boiling point of CH3 or CH3, which is polar molecule, is more than C3H8 with almost same molecular formula, but when it is non-polar. Okay, so let's move on to the next page. Okay, it says dipole-dipole attraction can occur between any combination of the polar molecules. It means it's not necessary to be in between the same molecule. For example, PCl3 is non-polar, CHCl3 is non-polar. So you can have dipole-dipole attraction between these two molecules, no matter if they are same molecule or not. So that's why polar solutes are soluble in polar solvents. So if you have polar molecule, most of the time it's soluble in the polar solvent, okay? Because both of them can have dipole-dipole attraction. So the solute attracts it to the solvent molecules, but this type of the attraction. And what is written here is important. It says for two substances of similar molecular mass, the more polar substance will have the higher boiling point. It says similar molecular mass, so the London dispersion force is same for both of them. But the polar molecule, because it has also dipole-dipole attraction, its boiling point is more than non-polar molecule, which doesn't have dipole-dipole attraction. Okay, another type of the attraction, which is combination of these two, is dipole-induced dipole attraction. Like when HCl and Cl2 attract to each other. Again, one more time, I want to show that one. HCl molecule is polar molecule. So if I want to draw, oops, let me change my pen. Okay, it becomes something like this. So this part of the molecule is partially positive, this part of the molecule is partially negative because it has more electron. Cl2 is non-polar. It doesn't have positive and negative area. When Cl, so this is Cl2, this one is HCl. When Cl2 come close to the HCl, because this area of the HCl is negative, it pushes the electron away from this side of the chlorine molecule. So this part of the chlorine molecule which electron goes there becomes partially negative, this one becomes partially positive. It means this one which has dipole induces the dipole on Cl2. So this one is induced dipole. Cl2 doesn't have dipole, but the dipole can be induced on that by adjacent dipole molecule. When this happens, there would be attraction between these negative area and this positive area of the molecule. This type of the attraction we call it dipole-induced dipole. This is very important when the oxygen dissolves in the water. Okay, the water molecule is polar. So in the water molecule you have negative and positive area. Oxygen molecule is non-polar. So the water induces the dipole on the oxygen. By induction, this area of the oxygen becomes negative, this area becomes positive, and there would be attraction between them. And that causes the oxygen to be able to dissolve in the water. This type of the force is weak, so the amount of the oxygen we dissolve in the water is limited. But it's very crucial for the living organisms which use the oxygen in the water. Okay, so let's go back to your book. Okay, so we finish up to here. Okay, let's talk about this one, van der Waals forces which are available. So the van der Waals forces is very general term, and it includes all of these three type of the attractions which you can have between the molecules. So it's London dispersion forces which are available between all of the molecules, and this is the only source of the for non-polar molecules. Also dipole-dipole attraction, which available only between the polar molecules, and dipole-induced dipole attraction, which available between the non-polar molecule and polar molecule. So to all of these ones, we call it van der Waals forces. And look at this last paragraph. It says in some cases, van der Waals forces, it means one of these three, may occur within a molecule. We call it intramolecular attraction. If the different groups can position themselves appropriately. So again, I want to talk about this one a little bit. If you have a very long molecule, okay, suppose you have a very long molecule like this. So this can be carbon, whatever it is, okay, and this part of the molecule is partially negative, this part of the molecule is partially positive, you can have attraction between these two parts of the molecule, okay. So it can be anywhere. For example, suppose this area is partially negative, this area is partially positive, you can have attraction between these two areas of the molecule. So here we have van der Waals forces within the molecule, intramolecular attraction, but this is not the bond, okay. So it's not the covalent bond, so it's not covalent bond. So it's only attraction which is available between these part of the molecule, and these attractions are usually weak. This type of attraction you can see in the big molecules like proteins, in the DNA, and in the sugar molecules, or in the polymers, which are the long molecules. Okay, so we finish this video here. In the next video we will talk about the hydrogen bond.